Hi guys, today we're going to be doing two sets of lecture notes since I'm not in class. We're going to do the data representation notes, which you're going to notice all the other periods are doing also. And then I'm actually going to cover data compression today as well, which is actually a set of notes that were for next week. The reasoning behind that is there's a fun activity that we were supposed to do in class today. We really need to have the teacher in class for that, so we're going to have to hold off on that activity. So I'm going to double up on notes today so that we have some time next week to do that activity. You'll probably hear about it from your friends in the other periods. It is a good time, but you can expect to do that next week. In any case, let's talk data representation. So here's the idea. Data representation is saying, okay, we now understand how we can represent numbers using zeros and ones. How can we represent more interesting data? So when computers are running programs, they don't just want to be able to represent integers. They need to be able to represent letters. They need to be able to represent strings, colors, sounds. That's data representation, talking about how we can come up with encodings that use binary digits to represent data. And that's what we're going to talk about in the next half of these slides or so. So let's start with bits versus bytes. We kind of already talked about this already. You've seen the slide before. But just remember the smallest unit of data is called a bit. A bit is a single transistor on your computer, basically an on-off switch. The switch can be set to off or on. We could have that off or on represent some interesting data, though. Off can represent the word no, while on can represent the word yes. Off can represent the number 0, on can represent the number 1, off can represent the Boolean value false, on can represent the Boolean value of true. So this is we've already started to talk about data representation. This is the simplest form of data representation. How can a single transistor on a computer represent some interesting data that we're trying to communicate or store? What we can do, though, is we can collect together a bunch of bits, say 8 bits, and call it a byte. And then a byte, or even a collection of bytes, can be used to represent more kinds of data, whether it's letters or whether it's colors or sounds. We'll see some examples over the next few slides. So first, let's talk about using bits and bytes to store data. So there's lots of different data that we like to store on a computer. Characters being the first. Keyboard characters, right? The letter A or the letter F or the letter 7 or a question mark. Positive integers. They're called unsigned integers because we're only allowing positives there, but 0, 1, 2, 3, etc. We want to be able to represent those using binary digits. Floating point numbers, decimals, like 1.21987. We want to be able to represent that decimal using bits on our computer. Colors, red, green, blue, and combinations thereof that make more interesting colors. Strings, a collection of characters or a string of characters, like the temperature is 79 degrees, or a sentence or a paragraph or a book, whatever the case may be. All of these different kinds of data, we call these data types. So there's many different data types that we want to represent on a computer, whether it's characters, integers, numbers, whatever. Let's continue. So with data types, it's really common for students to ask, why do we need to distinguish between different data types? It's all zeros and ones on the computer. What's the point of distinguishing between these different data types? The idea here is that data types might represent very different kinds of data, right? Colors and characters and numbers are all very different things. Therefore, we may have very different ways of representing that data as digital bits. They may have a different encoding. Basically, you're going to be receiving a string of zeros and ones when you download a file, and your computer is going to need to be able to look at those zeros and ones and interpret it correctly, whether it's going to interpret the zeros and ones as a color, or whether it's going to interpret those zeros and ones as a string or numbers or whatever. We need different encodings that tell the computer, hey, this string of zeros and ones represents the color red, while this strings of zeros and ones represents a novel that we're trying to read on our iPad, something like that. And then finally, the methods that we use to manipulate our data can be very different depending on the data type. We've already seen that example, right? Addition means two very different things when we're talking about strings versus talking about integers. Addition for integers is very straightforward. 9 plus 7 is the standard expected 16. While the string Bob plus the string cat would be concatenated, because the data type there is strings, to create the string bobcat. Those are very different data types, and there's different methods for working with those data types, which is why we have to distinguish. When you guys are doing a project for the College Board starting in late November through December, one thing you're going to have to do is recognize different data types. It doesn't get too complicated. You basically just need to know when you're working with strings versus when you're working with integers, which we've already talked about doing. We've already talked about parsing a string as a number if we need to interpret as a number. We've already talked about concatenating versus integer addition. So it won't be too bad, but it is something that you guys will be expected to understand starting around December at the latest. All right, continuing on with data representation, let's talk about encodings a little bit. And encoding is just a scheme or a system for storing and transmitting a certain type of data. Basically, it's like a code where you share the interpretation of that code with all of your friends and everybody online and anybody that might be encountering your data. You might agree that the binary integer 100 would be interpreted as the color red, while the binary integer 1010 would be interpreted as the color green, or something like that. That's what an encoding is. It's an agreed upon scheme for communicating a certain type of data. It's not the same as encryption. People will use the word encrypt and encode synonymously in popular culture. You'll see it in the news. You'll hear people talk about it in movies. They'll talk about them like they're the same thing. They're not the same thing. Encrypting is for obscuring data. Encoding is for clear communication. You're not meant to keep information secret with an encoding. It's a way of enabling communication using binary bits. I have a few examples. These are very just standard computer science examples of well-known encodings. The UTF-8 character encoding. You guys will see this anytime you browse the web. Anytime you request a web page from a server, basically anytime you type in a website and a web address and you press enter, the server is going to send you binary data. And your computer is going to interpret that binary data as many possible things, but often as characters, letters of the alphabet, that are encoded using the UTF-8 standard. It stands for Unicode Transformation Format, and what we do is we use 8 bits to represent a single character, whether that character is like a letter A, or whether that character is a question mark. There's a lot of possible characters, many more than we actually use. If you want to figure out how many different characters 8 bits can represent, what you'd want to do is you'd want to go into your calculator and compute 2 to the 8th power. And UTF-8 can store that many different unique characters. 2 to the 8th is a fairly big number. It's not huge, and so there are limitations. There are UTF-16 or UTF-64 character encodings for encoding many, many more characters, oftentimes to include characters from other languages other than English. Anyway, the only other thing I should mention about the UTF-8 character encoding is there's an older standard called ASCII, ASCII. When you guys see ASCII, that originally used 7 bits to represent a single character. Basically, that's when space was at a premium, computers were expensive, hard drives were expensive, and every bit counted. And so we wanted to squeeze as much data out of the smallest amount of space as possible. So we had 2 to the 7th possible characters for the ASCII encoding scheme, half as many as UTF-8. It was problematic because as the internet spread across the world and more people from more cultures, from more different languages tried to communicate, ASCII was limited. And so UTF-8 is the new standard. It has twice as many characters as ASCII, and there's even more encodings that encode even more characters than UTF-8. Anyway, moving on, 32-bit binary integers. Typically on a computer, when you store an integer, when you write something like var x equals 5, the computer will see that var statement, and it will reserve 32 bits in memory to store that integer. Now for the number 5, that's overkill, because the number 5 is fairly small, and 32 bits can store some fairly large numbers. But that being said, we reserve 32 bits in memory for any integer. Typically, there's other encodings, but a very common one is 32-bit integers. And it's basically just in case room. So we could allow numbers to get very, very large. You know, when you're setting timers that are counting microseconds, or when you're counting a score in a video game that gets very, very large, you need room for some really big integers. 32 bits can represent 2 to the 32nd power different integers. That's a lot of different integers. If you want to know the biggest integer that you can represent using 32 bits, it would be 2 to the 32nd minus 1. That's the biggest binary integer that you can represent using 32 bits. It's a really big number. You can try typing it into your computer or into your calculator. It's big, though. It's a very big number. And then true color, 18-bit color. We talked about that in class the other day. True color, 24-bit color, reserves 8 bits in memory for red intensity, 8 bits for green intensity, 8 bits for blue intensity. If you wanted to make the color white, you would set all 24 bits to 1s. If you wanted to make if you were going to do that in hex, it would be the color FF, FF, FF. That would be white. Maximum intensity for red and green and blue will make white. In contrast, if you want to make black, 0, 0, 0, 0, 0, 0, at least in hex. In binary, all 24 bits would be set to zeros. And we did this in class already, but 24 bits can represent just a little bit more than 16 million colors, and you get that number by calculating 2 to the 24th power. All right, let's keep moving along here. Here's a little bit more about ASCII versus UTF-8. I already talked about a lot of this, so I'm just going to kind of breeze through it a little bit, but ASCII is an older encoding, uses 7 bits for characters, possible 128 characters, because 2 to the 7th is 128. That's a pretty limited number of characters. That was okay in the 1960s, particularly when computers were typically just communicating between two people that were speaking the same language with the same character set. And that happened because storage was really expensive in the 60s. In the 90s, computers started to get a lot better. They were able to store more data. They were able to transmit data more quickly. And so we upped it to the UTF-8 character encoding. It turns out, though, ASCII and UTF-8 are the same encodings for most of their values that you would see on a regular basis. UTF-8 added an extra bit of padding on the left-hand side with a 0. So if you want to convert from ASCII to UTF-8, you just add a 0 to the left-hand side of your ASCII character. But what that allows us, when you add one more bit, you double the number of characters. So 2 to the 8th, 256 possible characters. So for characters that were missing, you would start them with a 1, and then you get double the number of encodings after that. It's used on about 90% of all web pages. So about 90% of the pages you visit use UTF-8. There are other standards, particularly in countries that use a different character set than we do in English. UTF-16, UTF-32 are a good way to go because you can store many, 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 many more characters that way. Here's an ASCII/UTF-8 table. Technically, this is a UTF-8 table, because if you were to count up the number of binary digits there's 8 of them. So technically it's UTF-8, but if you were to drop the padding at the zeros, the leftmost 0, that would convert it to ASCII. So anyway, this is kind of the first start that you would need to be able to read binary digits as letters. You can already start to come up with quote-unquote secret codes. They wouldn't really be secret because UTF-8 and ASCII are well known, but you could theoretically write an email to a friend or a family member or something using 1s and 0s, and in theory they should be able to take those 1s and 0s and translate them 8 bits at a time, 1 byte at a time, to the appropriate letters. This link right here, you can get to that link on Schoology, and you can get the full set. I only gave the first, I don't know, 100 up to 111 or so. And actually I cut out some control characters at the beginning as well. I started at 32 and went up to 111. This is a partial list because these are the commonly used letters in the English alphabet and punctuation. There's a lot more than I could fit on a PowerPoint screen right now. Finally, these are notes from next week. You're hearing these early. We're going to talk data compression. If you need to pause for a quick minute and kind of catch up on the stuff that you saw on the previous slides, feel free to do that. You're listening on your iPad, you're using earbuds, so you can go at your own pace. But it is important that you get these data compression notes because I'm not going to do this lecture next week. I'm doing it now so that we can do a fun activity next week. You'll see. You're going to have friends in other classes, then you're going to see a little art project that they did. We're going to do that little art project next week. All right, so let's talk about a commonly used quote-unquote law that you will see written about in newspaper articles. You'll see it on TV. You'll see it in movies that talk about computers. It's called Moore's Law. Moore's Law is kind of a misnomer. It's not actually a law. It's a historical observation. But here's how this historical observation worked. What has been noticed from the 1970s to present is that computers are getting faster. In fact, they've doubled in speed about every 18 months or so. What that means is the iPhone in your pocket, because of all the doublings that in speed that have happened since 1970, the iPhone or the Android phone that's sitting in your pocket right now is way faster than the computers I used when I was growing up. It's kind of crazy. The phones in your pocket are faster in some ways than the supercomputers that the military and the government would have been working with in the 1960s and 70s. It is an important caveat that I should throw in here, though. So Moore's Law will eventually run into a problem. The problem being that there is something called physics, and physics has sets of laws. Transistors on computers, we've doubled the density of those transistors every 18 months. But you can only fit so many tiny little nanoscopic microchip, only so many switches on a microchip. Eventually, the laws of physics are going to catch up and say, hey, you can't make a transistor any smaller because that's smaller than the size of an atom. You also get weird quantum effects at some point. You need electrons to behave in a very certain way in a circuit. And if you shrink things too small, electrons start to act a little bit more like waves than like particles, and you get weird effects happening. So anyway, eventually physics will catch up, and Moore's Law will grind to a halt. Nobody knows exactly when that's going to happen. It's still going strong at this point. But my point here is that storage matters and efficiency matters. It's not true that you can just ignore efficiency in your computer programs and just ignore how much storage you need for a computer program because eventually computers will be fast enough and have enough storage. That's not actually true. Eventually, we're going to get to a point where we have to be very, very careful with efficiency of our algorithms, how quickly they run, and storage, how much space they take, because our computers are going to be hitting some limits. Along those same lines, at the moment, storage is getting less expensive. So along with Moore's Law, the cost per gigabyte of storage has been going down. Storage is cheaper than ever today, right? You can buy an iPhone these days that has more storage on it than was available on the entire planet in, say, the 1960s. I don't know the exact number on that, but it's going to be somewhere around there. There's so much storage on your phone in your pocket right now that back in the 1960s or so, that would have been all of the cumulative storage on the entire planet. But just because storage is getting cheaper than ever, we also store more data than we ever have. And we are expecting that at some point we will hit some limits in terms of how much data you can pack into a certain amount of space. Look at how much data we stored in 2016. 16 zettabytes of data. That's a lot of data. By 2025, we're expected to store a new 163 zettabytes of data. Well, that means that just because storage is getting cheaper, we store a lot more data. So even though we could store a lot of stuff, the amount of space that our programs use and the efficiency of those programs still matters. This is along the same lines as Moore's Law. Moore's Law is computers are getting faster at calculating things. This slide is about how storage is getting cheaper, but there is going to be a limit to that eventually. That brings up the need for data compression, the process of making a file smaller. We have limited amounts of storage on our computers. We have limited amounts of storage on our phones. So if we can compress our data, they might take up less space in memory. Also, a lot of people pay per gigabyte on their cell phone plan. When you're using your smartphone and you're watching videos or you're transmitting data, the amount of data you use typically translates into how much you have to pay on your phone bill. Well, if you can compress your data before you transfer it, it doesn't take as much time or bandwidth to transfer, which is good. So data compression is useful. We need it. We can't just ignore compression. The idea here is what I just mentioned. Hard drives cost money. Your iPhone or your Android phone has a limited amount of storage. And we usually have to pay to transmit our data. And so compressing helps on all of these fronts. Each of these things gets better when our data is compressed. We use less hard drive space. We spend less money on hard drives. We don't need to buy a phone with as much storage. We don't need a cell phone plan with as much bandwidth on it. There's two kinds of compression, lossless and lossy. They both have their purposes. Lossless is nice because it's reversible. The compression that you do, you can undo. Whatever compression you apply the compression, you transfer the file, and then you uncompress it on the other side, and that file is exactly the same as it was at the beginning of the transfer process. Lossy compression, you guys have all run into lossy compression before. Lossy compression is where information is discarded in the compression process. If you've ever watched a video on YouTube when it's kind of buffering and you have a bad connection and everything looks pixelated, well, that was lossy compression, and too much data was discarded when that happened. When lossy compression goes well, we discard information that's beyond human sensory abilities. Why store 17 trillion colors when the human eye can only distinguish between 16 million different colors? So you try to throw out data that is not going to matter to a human anyway. They don't really care about the 7 zettabyte video file versus the 7 gigabyte video file, because to them they're going to look identical, because the difference between the quality in those two videos is not something that humans can even detect. Another thing that's nice is lossy compression is useful when you are willing to sacrifice quality in order to save storage space or bandwidth. If you have T-Mobile, you might experience this. There's a plan for T-Mobile. I can't remember the name of the plan, but basically you get unlimited YouTube videos and streaming videos from a bunch of other websites, but it's a trade-off. They give you unlimited videos from all these different websites and apps, but they're only sending you the video at a lower quality. And so a lot of consumers are willing to sacrifice some quality to save some storage space or save some data on their phone plan. And the other problem with lossless, or lossy that is, once you've done lossy compression, you're never going to reverse that process. You have discarded data that you are never getting back. Google Photos does this. When you upload pictures to Google Photos, the default setting is to apply lossy compression to your pictures, and they give you unlimited storage if you do that. The idea there is they throw out a very small amount of data, but they're able to store a lot of pictures for you without it costing them a lot of money, so they give you unlimited free storage. You're making a trade-off there. You're saying, hey, I'm willing to give up some bits of data, and I'm kind of banking on the fact that I'm never going to want to take this picture I took and blow it up to the size of a billboard or something. You try to blow that thing up to a billboard size, and it's going to look pixelated. You're going to see the data that you've lost. Here's an example with lossless compression. Really simple. Look at this string right here. A, B, 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 whatever. A bunch of repetitions of A's and B's and C's and A's and E's and F's and D's. Well, A really simple encoding scheme here, compression algorithm, would be to say, hey, I have 3 A's in a row. Let's just write A3 to represent, I'm going to write A 3 times. Look at all these B's. If you count them up, there's 8 of them. So in our compression algorithm, we could say B8 to mean repeat B 8 times. And as long as you're communicating with someone who you've shared this encoding scheme with, this is going to make perfect sense to them. And they're going to be able to uncompress the file, and they'll be able to recompress the file back and forth without any loss of data. There is a couple interesting ones here. Look at the letter E. I did not write E1. The reason I did not write E1 is that would actually increase the amount of storage that it would take to store the letter E. So if there's just a singleton, a single letter on its own, just write it on its own, don't put a number after it. Same thing with 2. Well, FF, I mean, I guess we could store that as F2, but it's kind of redundant because F2 would map to FF. So you did extra work to convert FF to F2 just to convert it back to FF. So when there's 2 instances of a character, we just write the 2 instances of the character. So basically the numbers are reserved for if there are more than 2 repetitions. And this is a perfectly valid lossless compression scheme. And it's not that far from the sort of stuff your computer actually does. Lossy compression, in contrast, is discarding data. It's saying, hey, you know what? We're going to play a sound at 1.9 or 0.198 megahertz, let's say. And then someone might say, oh, but the human ear can't actually detect the difference between 0.198 megahertz and 0 megahertz. So let's just round that down to 0. I'm making that up. That actually doesn't work with sound exactly right like that with those numbers. But that's the basic idea. We have some kind of data that we can round everything. You can see that rounding happening. We're rounding things that are close to 0 to 0. Things that are close to 30 are getting rounded to 30. And we have compressed that data quite a bit by running that algorithm. The problem is you're never going to get back what you started, right? You're never going to get back to 0.198 or 29.01. So you are making a trade-off there, but oftentimes that trade-off is worth it if that sacrifice in quality is not something you would even ever notice. There is one name of a compression algorithm that I am expecting you guys to know. I don't expect it to be on the AP test, but anybody who takes a course in computer science that talks about data compression should know about this family of lossless compression algorithms. It's the Lempel-Ziv-Welch family of lossless compression algorithms. It's not that different than the example I showed you 2 slides ago. You're looking for repeated patterns in your original data and compressing down those repeated patterns. The reason I think it's worth knowing, both for like the exam that we take in a couple weeks and just for this course in general, is that family, the LZW family of compression algorithms, led to the zip file format, which we've used quite a bit in this class. Image compression. I've got a couple examples here just so you can get your feet wet with this. So when you are storing or transmitting pictures, images, you have a couple choices. You could do no compression. It's the fastest way to access your data, but it takes up the most memory. A bitmap, a .bmp, is a classic example of just no compression at all. Don't compress the data, just store it as is. That's what a bitmap does. Lossless compression, there are 2 examples. The graphics interchange format, known as a GIF or a GIF, depending on your personal opinion on that. There's disagreement on it. And then the PNG, portable network graphics. These are 2 lossless compression algorithms. They're really good on like cartoon-like images. Because if you have a cartoon, think about your favorite cartoon show. There's a lot of identical colors, right? When you see a cartoon character, their clothing is probably all the same shade of red or all the same shade of brown. Well, that's really good for a compression algorithm that's lossless, because we could say, hey, look at all of those red pixels in a row. Just say red 50 times or something like that. Lossy is better on photographs. So lossy compression, it's really good on photographs because there's a lot of small color variations in the real world. Unlike a cartoon, when you take a picture on your phone, there's a lot of color variation in most things that you look at. So the JPEG lossy compression format is a pretty good way to go. And then finally, there's vector formats. We're not going to talk too much about that, but this is kind of like geometry class in a file type. Store relationships between polygon shapes instead of pixels. They're really neat. Vector formats are awesome for things like video games because they're infinitely scalable. So you could make a video game that will look just as beautiful on a smartphone as it will on a billboard-sized screen. So that's what a vector format does. If you ever see an SVG, a .svg file format, that's a vector format. They're on Wikipedia a lot. You don't see them too many other places, but they're really neat. I have an image compression example here. So here is a little comic book logo that I found. And it has no compression. It's a bitmap file, and it's about 9,000 kilobytes. When you apply compression to it, when you do lossy compression, I can get this thing down to 117 kilobytes. I am discarding some data, though. But you are going to basically use this lossy compression algorithm and throw away some data that you think that nobody's going to notice, and you can actually get the file size a little smaller. Now, lossless compression here for this particular kind of image, because it's cartoon-like, a PNG actually ends up even smaller. Even though it's lossless, we can get it down to 47 kilobytes. There's a lot of repeated pixels, so you basically would say something like black pixel 5,000 times, yellow pixel 6 times, whatever. And because of the nature of this image, in this particular case, lossless is better at 47 kilobytes. If you have a photograph, it'll often be reversed, where the lossy compression will be smaller and the lossless will be larger. Depends on the example, depends on the picture, but that's the general idea there. I do have a picture here where you can see the difference. A JPEG has what are called artifacts. Basically, if your loss of data is large enough, you can get some visually apparent problems with the image. Compared to this lossless PNG where everything is crisp and we have not thrown any of the original data away. If you see any imperfections in this image, those imperfections were in the original image before the compression. You're seeing the image as it was created, compared to the JPEG that has a lot of problems. It's a trade-off. If you don't care about that loss of data, then a JPEG is a good investment. Audio compression, there's 3 different options here. No compression, there's 2 file types, a WAV being the most, a WAV being the most popular. Lossless compression, any audio files who love listening to high quality music will have heard of a .flac file, .flac. They're not too common outside of people that have really nice stereo systems or like to listen to like perfect recordings of music, but that's what a .flac is. And then the most common file format is the lossy compression of an MP3. The nice thing when you're talking about an MP3, oh, actually this says an MPG. That should have said, I'm surprised they caught a typo. An MPG is a video format. Supposed to say a .mp3, sorry about that. Anyway, an MP3 is supposed to throw away audio data that most people are not going to notice anyway. The idea here is the human ear is not perfect, and your speaker systems usually are not perfect. And so there's a lot of data that you can throw away with very little consequence most of the time. There's going to be an exception to that if you are at a movie theater and you're watching an IMAX movie with perfect Dolby surround sound. You're probably not going to want to use lossy audio formats on that because you might notice the data loss. But for most purposes, lossy audio is great because we're just discarding sound data that the human ear or your earbuds would have never even noticed. Next time we're in class, we'll look at an advertisement from a company that's marketing in a lossless audio format, and we can kind of listen to some differences between the two. But I'm not going to do that right now because it's kind of hard to show a YouTube video inside of a YouTube video. So continuing on. If you guys are really into this, there's a couple links you can click on Schoology for further viewing or further reading. This is great stuff. If you are interested in compression, if you're interested in data, if you want to be a computer scientist or engineer someday, or you even think you just might be curious in taking some more of those classes, these links are great. You'll learn a lot more than you did in this slideshow, because this slideshow was just an introduction. Some of this will get more into the nuts and bolts of those compression algorithms, which is very interesting stuff. The other thing that I think is a great idea is at home, open up a photograph in Photoshop or your favorite image editor and do some experimenting. Try moving some pictures between different file formats, a PNG, a JPEG, a BMP. Look at the file sizes changing. Try to zoom in on the picture and see if you lost any data when you converted to a JPEG. The best way to get a feel for image compression is to experiment with it and look at those images, zoom in on the images, look at the file sizes of those images. Compare a picture with a cartoon, a photograph with a cartoon. Look at which compression algorithm is better for that situation. Anyway, guys, have a great day. What I'm going to ask is if with any extra time you might have, there is that programming task that is due tomorrow, Thursday morning at 7:30 a.m. That would be the color exercise, the RGB hex color example that we were working on in class. That is due on Thursday. And there is a multiple choice number 6. It's in the older folder. It's in last chapter's folder because I shared it with you guys early. Multiple choice number 6 is homework for Wednesday night, due Thursday morning at 7:30 a.m. Have a great day, guys. Thank you.